Well, hello, everybody. I'm Mike Brown. I work for IBM, work on Container D. I've been around for a long time. In the good old days, I used to work on operating systems, something called OS2. You might have heard of that. DOS, back at the beginning. Went on to work on Java virtual machines for a few years, did the IBM JVMs on a whole bunch of various platforms, including the first one on Linux. I got to rewrite the core of the JVM, make it really fast, change how semaphores work, all that kind of stuff. Had a lot of fun in JVMs, and went on to work on WebSphere and did a lot of telco stuff. Basically, I've been in IBM for a long time, working on a lot of systems code. Before I joined IBM, I was a programmer doing pretty much the same thing you guys would be doing for insurance companies, right? A lot of fun. Ran my own software company for a while, and came to IBM, and been doing open source for now 4 years for IBM. We started out with Docker, or at least I did, and then after Docker, I started working on Kubernetes for a while. In the meantime, I was working on the OCI committee. I was working on Run C. Been doing specifications. I'm a maintainer as well on the distribution spec that we're working on. So if you're working in OCI, you'll probably see me around, or at least on the calls. We get together a lot. So Container D is, it's got a long history, it's sad. The beginning of Container D, what was happening is Michael Crosby was trying to split up Docker into a bunch of layers. So a little bit easier to manage, a little bit easier to service, as well as to start to come up with this pattern where he could outsource or open source, some of the componentry for libcontainer, the libraries that make Docker work with Linux. So he wanted to make that open source as well, outside of Docker, so that other people could build products like Kubernetes or anybody else who wanted to put together a container runtime platform could be able to do so with the same code, so that we weren't forking everywhere and creating too many different models for Docker containers. Didn't want to have bifurcation in the field. So he put together this Run C implementation, which was also provided to the OCI spec. So if you go look in OCI, you'll see where Run C lies. It's in open containers. It was donated by Docker to the OCI team, and that's where it lives. A little bit later in time, it became clear inside of Kubernetes that we needed an API to interface with the various container runtimes, because there was a version of kubelet for Docker, and there was another version of kubelet for Rocket. You might have heard of Kubernetes, and every time Docker made a major change to an API or whatnot, Kubernetes would go down, and Tim would have to come talk to the Docker guys, and every time try to keep things in sync, because there was no real specification for what Kubernetes needed from a container runtime. Right? So this container runtime interface concept was getting put together because Michael had already started splitting the layers of Docker out. He was able to create an initial Container D model that would start to, hopefully at some point in time, host these container runtimes interfaces that would come in the future. But until that would happen, there was a thought that maybe we could do a container DSHM or something like that, instead of having kubelet run the Docker DSHM. I figured maybe we need less instead of the whole big full Docker product, right? So they came up with the idea of the snapshotter interface and having its own content store API inside of Container D. The Container D client API is really cool. You can write a small Go program and create these service interfaces with Containerd with just maybe 50 lines of code and run your own containers. So there's been a lot of people starting to use the Container API as an application, and they're using these interfaces. So after the initial 1.0 of Containerd, which was really just there for Docker only, we started building a CRI implementation that was Lantau and me that would actually implement the CRI interface. We did our own daemon in the beginning. It was called Cry Containerd, and it would call the Containerd client interfaces from remote. So we had a gRPC interface between kubelet down to Containerd, and then from Containerd CRI to Containerd itself proper. So we had 2 hops. At that time, the Containerd guy said, hey, let's create this plugin interface so that we can extend Containerd's capabilities, and maybe in some future point in time, bring the Cry guys inside of Containerd so that it's a plugin that's already built in, instead of having 2 daemons. So around that time, Cry implementation goes alpha. Our product was working. We got all the test cases to run for Kubernetes when it's running on the Containerd through the Cry Containerd thing. Okay, so then we went beta. We built our plugin. We released it. Everybody's happy. Time goes on. We stabilized. We started seeing a lot of clouds creating some interest. CNCF has now graduated Containerd. We're now being used by quite a few clouds. IBM Cloud's using it. So today, if you create a new cluster on IKS, it's using Containerd by default. Google Cloud is also using it, GKE in production, and with gvisor, you have options. Alibaba Group, we have Fuwei, who is a new maintainer for Containerd, although he's been involved for a long time now, but he'll tell you about Pouch, and Pouch is using Containerd. Alibaba, if you don't know, is China's Amazon. Okay. Speaking of Amazon, so we've been working a little bit with the Amazon guys. They've built a Firecracker implementation that it's a container runtime engine. I know this can get confusing. We have container runtimes, and then container runtimes use container runtime engines like runc or a virtual machine in this case, which is Firecracker, to create the isolation layer. If you went to an earlier pitch with Phil, he showed you how you can set your runtime class in your pod spec YAML to pick which container runtime engine you'd like to run. And you configure Kubernetes to pick the container runtime. Okay. So this is the eye chart, right? We're showing the platforms at the top, systems, architectures at the bottom. It runs on just about any Linux platform. We do pre-builds, images for everything from ARM to Ubuntu or whatnot. We do a lot of tests. We run Cry tools, test validation suites. We run the Kubernetes cluster suites. Every pull request we do actually gets shadowed up to the GKE to run on GC to run the full suites of tests to make sure that we don't break anything. And then of course the Docker team forks our tree, and they build their own version for testing. You can get your distribution of Containerd now from containerd.io. Just do apt-get. It's all available. Or you can get a Docker, and because Docker's depending on containerd.io, you'll pull that down automatically for you. Most of the distributions are starting to ship with Containerd as well. Some by default, so you'll start to see that it's easy to install because it's already there. It's really nice. as far as clients go, the containerd itself, it has this client interface, but it's not trying to replace Docker. It's not trying to replace kubelet or kubectl or anything like that. It's more of an infrastructure component. We do have some client APIs, some tools you can use, but again, we're not trying to replace command for command what you can do with Docker. For example, we don't do builds from within containerd. So if you want to run a Docker build, you do your Docker build. But if you want to do a pull, you can do a pull image from Docker, or you can do a pull image from containerd using either the CryCTL API, which is common for all container runtimes, or you can use the CTR command line API tool, which show that. Maybe we'll show you that a little bit later if we have time. You'll notice the architecture. It's very extendable. It's very pluggable. When you go look at the config for containerd itself, it has a list of plugins that you run. Everything is pluggable. Everything's modifiable and configurable. You could, for example, Docker's initial distribution ran without the CRI plugin being enabled. So I got a lot of calls the next day saying, containerd stopped working because when they installed Docker installed containerd, and it didn't have the CRI plugin installed and running. So when you ran Kubernetes, kubectl pod apply, it didn't work because we weren't running anymore the plugin because they had disabled it. For Docker, they didn't need CRI at the time, but our other implementations did. So you just go out to the config file and change it to say, CRI enabled, yes, and that seems to work. We support metrics through Prometheus compatible API, stats collectors. I mentioned earlier, we've got our own snapshotters. It's actually pretty cool. Steve-O put together most of the work on it, and then Jerk McGowan has been working on it a lot lately. We're getting contributors, providing additional block native snapshotters. We got all the usual overlay, BTFS. I use overlay usually. The content stores the API that the clients use to gain access to storage, as well as metadata, and everything's done in we're in its own little namespace environment. I mentioned earlier that Docker can use containerd and Kubernetes can also use containerd. Well, you can also create native local containers within containerd, and it starts to get a little confusing. So we created a brand new namespace type that isolates when you're in. You want to create images and containers and pods. For Kubernetes, you would use like a k8s.io namespace. If you use a Docker container, it'll be in a Moby namespace if you're CE, or it'll be Docker if you're E. And you can create your own namespaces. So if you're writing your own little application container launcher, you could just say, my namespace, and that way when you do a listing of containers or pods from kubectl, you won't see any containers that weren't generated from your kubelet. Instead, you'll see just the containers from the namespace you picked. So we think that's pretty cool. So in this way, we can have one common layer, daemon sitting there waiting for containers to be created from all these different places, and got some pretty good use cases for that. Down here at the bottom layer, depending on what type of runtime you want, you can pick to run simultaneously in all these different namespaces, run C containers, Kata containers, Firecracker, gvisor, pick your isolation layer. I've got my favorites. You might have your own favorites. I think we're going to change things over time so that we think you'll want more container isolation than less. If you like VMs, that's okay too. Like, for example, one of the things we're doing today, when you create a pod, you get a shim for each container. In the future, we've got a fix where you'll actually get one shim for the pod, and all the containers are isolated within it, so we use a lot less memory. It'll be faster. Akira Suda, he was there a minute ago. Curiosity put together this rootless stuff. You'll see more isolation on containers that way by picking the namespace you want to use instead of it being the root namespace. So if you get a container exit, it's isolated within that namespace. We haven't seen many container exits. So client server design, we use gRPC, which was put together by the Google team. I think that's why it's Google G. I think it's Google's RPC. But it's just a long story, I guess. It's written in Go, the implementation that we're using. Seems to be working pretty clean. We also have a thing called tRPC, which we use between the shims. It's a very thin version of gRPC. It's a lot faster, a lot less memory requirements, so that we don't have any issues with all the shims we might create. The shims are used to host your netproc in your container, so you can grab the return code, as well as to be able to create streams between for I/O, standard I/O, standard in, standard to the API server through kubelet. So if you want to get a command line and do an exec, you can get it through there. I mentioned earlier we have a metrics API. You can grab stats. Pretty much any tool that wants to do metrics seems to be compatible with Prometheus these days. So we went that way. So backend, I mentioned the ttrpc, but we're using it locally because we're a built-in plugin. So we have a low-level wrapper to all the APIs. You see here the different types of API. There's a metadata service, an images service, a container service. The main two services within Containerd are the runtime service, and the other is the image service. So you can, if you had your own tooling or whatnot for grabbing images, and you didn't want to use the local cache or whatnot, you could replace it, and some people have, so they can use their own native image retrieval code. But then when you create a container, you can use the Containerd default interfaces for like using runc or VMMs via the v2 shim API or the v1 API. V1, V2. V1 was the initial shim API that we used to launch runc. There were a lot of people that were writing runc implementers, like runv, the vertlit guys. Rocket was working on one. A lot of different runtimes, but the Kata guys came in and they had hooks, and it wasn't working very well. runc has these hooks where they'll grab the exit or the enter code on any container that's get launched, and it would call this little program, and they were having, but anyways, long story short, the V1 API wasn't really a good one as far as extending the capabilities. So again, Michael Crosby, he keeps coming in and being the hero. He came up with this V2 shim API that all of the Kata guys liked, and it also runs runc, and then the V2 shim API is this new layer. So at the top, you've got the container runtime interface layer, and then your container runtime runs, and then in order to execute a VM or your container, you need another API layer, and then we call that the V2 shim, for want of a better name, right? How are we doing on time? Okay. So snapshotters, mentioned it earlier. It's actually a pretty cool interface. The same guys who wrote the Docker storage code wanted to refactor it and clean it up, make it faster, and that's what these guys. It was Steve-O. I don't know if you have Stephen Day. He's still a major contributor. He's a maintainer. He put it together, and we've got a lot of other good Docker guys that are working on this. They're focused on it. They're doing some work, I believe, to put Docker on the Containerd snapshotter systems as well, snapshotter interface. a basic diagram of, copy on write type, what snapshotters do. So, I mentioned earlier, CRI, we're a plugin interface. So Kubelet talks directly to our gRPC CRI interfaces. We just configure, you say extern, and you point to a Docker, to a socket, and Linux socket, and we host the gRPC services. You can talk to CRI directly, and that's what CryCTL does. Okay, over here you'll see CNI. That's how we do our networking. We support all the plugins. We've got a lot of good debug stuff we're putting in to help you guys set up your network and see what may be going wrong in the plugins. But for the most part, once you create a pod, we instantiate a new network interface for the init proc for that pod, which is a pause container. And then we'll share that namespace, that network namespace, with all the containers inside that pod. Okay. Is there time for demos? What time do you guys got? Let's see. Go ahead. All right, let's show. So what we got here is just my laptop. I'm running VirtualBox. What's that? Oh, well, that's no fun. I didn't change the resolution. Maybe quit my PowerPoint, maybe? We were having difficulties earlier. Try that. Hey, all right. Yeah, now my VirtualBox doesn't want to display. It's not displaying on my screen either. Let's try that. Pause. Hey, all right. Okay, so I've got Kubelet up and running. We use kubeadm to launch a cluster, single node master obtained it, so that just got one node and one master on the same machine. Let's see what we're running here. Can you see the text? Big enough in the back? All right. So you can see here we've got Nginx running inside of a container, inside of a pod, inside of a cluster on my virtual machine, on my laptop, and a standard development environment. Right? Let's see, we can do an inspect. We've got shortcuts, so you don't have to type in the whole ID. Let's pipe that to less. So you can see I've got some interesting tools that will show you a lot of data. We can see our IP address that we're using for this container for Nginx. So we'll go ahead and copy that. I think one of the interesting things, because it's open source, if you guys need anything additional in the specs, just open an issue. We'll add it real quick for you. I mentioned earlier I'm doing some cool debug stuff right now for all the plugins for CNI. So I should be able to do a curl. No, we'll just paste it. You can see it's talking. So I did the inspect, grab the IP, do a curl. We should be able to check the logs. What was that pod? Let's see here. Container. So I'm going to grab the logs from that container. I think I could have just said -p. Hold on a second. We'll grab the log directly from the container first. -p, yeah. Yeah. Oh, you think? Oh, anyways. Let me see. I'm always forgetting these commands. I run most of the test cases. So let's see. If I were to do, yeah, just container ID. Yeah, it should have worked. Yeah. 78. Oh. Anyways, yeah. So that's, you can see the recent curl request. So that's cool. So if there was an error, it would have popped up in there. So that's one command line. I mentioned cryctl. The way it works is it's just talking to a socket. Cryctl is pretty cool. It's a little group that's got together and tried to put together test, not just a command line interface, but also a bunch of test buckets. Again, to keep it run against the container runtime. So every time we ship a PR, we run cryctl validate, and we can add test cases. We try to make sure everything's running fine. All right. I think that's enough. Anyway, so CTR, if you want to play with that. Anybody have any questions? I just want to rambling up here. Any questions about container integration with Kubernetes? No? I have a question. I can hear. Yeah.
Okay. So what will be the difference to interact with your pod using .ctl instead of using kubectl? Because I see dual display logs as you display log with kubectl. You can also inspect IP from the kubectl. So what are the plus for those?
Well, if you're used to using Kubernetes, just stick with kubectl, right? The inspect just calls down to the CRI and does the inspect from us. So when you look at the actual log output, you'll see the initial set of kubectl inspects that you would expect to see from the Docker shim. But then at the bottom of that, you'll see an extension point where we'll just give you a dump of everything you have. For example, if you're inspecting a pod, you'll see the pod specification. Okay. The pros and cons in kubectl is the standard API for all container runtimes. I think if you were doing some debugging, you weren't getting the information you needed from kubectl, then you might want to step down to cryctl and use it. I wouldn't use cryctl to launch a pod in Kubernetes. That's not going to work because then Kubernetes wouldn't know about it, all right? So it really comes down to the layer of where you're at, in the stack.
Okay, I understand. Yeah, I think I have one of those use cases because sometimes when a pod crashes, you don't have useful information on the kubectl side. You have to go deeper. I used to inspect those using Docker directly over the node. Yeah. Right.
Good point. So you wouldn't be able to use Docker's command line interface to interact with any pods you've created, but you can use CTR to interact and get more debug information, on those pods that are still there but haven't been destroyed yet. You can go inspect them. You can actually even attach and look at the trees and.
Thank you.
Right. So yeah, that's a good point. Yeah. I wouldn't use cryctl for that. I'd go right to CTR, I think. Just it'd be the low end for both products, for Docker and for Kubernetes. But again, only if you're a programmer and you're debugging. CTR is a very low level interface. It's a little hard to use, but.
There's leases in the help output of the CTR. What kind of leases are these?
I'm sorry?
Leases.
Leases?
Yes.
No
There's.
comprende?
Yeah, lease. I don't know. In your CTR help output, there's a in the menu.
Oh, so the CTR what?
Lease.
Oh, list?
Not list. Lease.
Oh, a lease.
Yeah.
A lease for what?
That's what I'm asking. What are they for?
Oh, a lease. What the heck is a lease? Manage leases. I don't know.
Okay.
What did they put in there? Let's find out. Sudo CTR leases. I got to find out now.
Okay.
List. That didn't help, did it? Yeah. I don't know. Let's do an LS. Let's find out.
Yeah, and I think list is like a log, and in the community, we don't provide a general purpose API in the server side, right? We will do a lot of things in the client side. So we might touch a lot of service. So we need to maintain a transaction. So we need a list to log the resources. So avoid to someone to delete something. So we can use the list to log one transactions. So something like when you try to put an image, you need to download the data into the content service, right? And you need to unpack into the snapshot. So this is long transaction. So we need a list to log those things. So after action is finished, we will delete the list. So list is yes. Yes.
So it's hooked up to the snapshotters.
Yes.
Okay, that explains it. Yeah. I work on the CRI side. I do all the integration and the networking, but I don't handle the file system stuff. That's Derek McGowan and other people. We have 18 maintainers.
Can I make containerd have a CRI listener on TCP socket and make everything work? So not using Unix socket, but TCP socket.
We're using a Unix socket.
Yeah, but can I use...
We could probably, that's what gRPC is hooked up to.
Okay. So I can technically have kubelet on one node and containerd on another node, where this kubelet controls the containerd on another node.
Well, it's all local. Yeah. So it's so everything I was talking about today, it's all on a node.
Yeah.
Right. It's all local host. So yeah, just a local Unix socket.
But is there like some hard requirements that kubelet and containerd be on the same host, or?
Yes. Yeah. Today, in the architecture, you get on one node, you have an instance of kubelet and you have an instance of kubeproxy running on that node, and then kubelet talks back to the rest of the cluster servers, like API server, to negotiate. Hey, I'm over here on this node. I can host these resources. That sort of thing. Okay. Yeah. Did that answer the question? Maybe. Maybe after talk a little more about that part. I love questions, especially the ones I can answer. That's okay. You catch us on Slack. Let me see. Just say hey, whatever, and we'll answer questions. We're in the Docker community Slack right now. If you want a better place, that's where we started. That's where we're gonna stay for a while. But yeah, so come on up there and hook up to container dev, containerd, or and pop questions if you want to. Especially if you want to write plugins or extensions. We're always looking for new extensions. We like that. Okay. Or if you have a problem doing configuration or whatever, we'll help there too. Okay. A lot of guys to answer a lot of questions. You don't have to go to GitHub if you don't want to. All right. Just come up and chat. All right. Thank you. I'm going to turn it over to Fuwei, our brand new maintainer from Alibaba.
Okay, it's my turn.
Thanks, guys.
No, it's... Yeah. Yes. And Miro. Use Miro. Okay, got it. So, okay, my name is Wei Fu. I'm software engineering in the Alibaba. So, thanks for joining me. And today we will dive into the containerd architecture. And I will show you the way about integration with containerd. So at the last session from Mike, we learned so many things about the containerd, right? Including history, status, architecture, overview, and demo. So we know containerd is the production-ready project, and there are so many kinds of company using containerd in production, and containerd runs very powerful and stable. So before we get into the real detail, let's recap the architecture. Wait, hold on a second. Use the point. Okay, it's the whole picture here, but let's focus on this area. So we know containerd provide a gRPC service to the user, so user can use the gRPC service to build any application on top of it.
So you can see this area. And there's some application based on containerd. And for example, Docker engine, pouch container, and the build kit. So unlike as usual, containerd doesn't provide a general purpose API in the server side, like a pull or push. So who's gonna provide general purpose API for us to make the integration easier? The answer will be the smart client. So in containerd, every component will maintain a very low-level resources like image local storage and image load data and a container configuration. And they provide a very stable and reusable API. So containerd will mirror the internal components interfaces to the gRPC interfaces. So for the client, they can access to any kind of resources by the gRPC call as they want. So for the common requirements, the smart client will combine several components together to provide a general purpose API, like a pull or push. So I think you might read the README and you'll find out you can just write one line code to download an image, like a pull function. It's very convenient and very simple. But behind the pull function is not that simple. So let's check out. There's the data flow for the pull function. We can see the client will touch four component service here. And first one is the content service. And it is used to store the raw data, such as the image layer tuple file. And the second one is the diff service. It is used to read the raw data and unpack the raw data into the local storage, such as overlay and the device mapper. Those local storage which handled by the snapshot service. And the last one is the image service. And it's not provide a pull function. It's just used to store the metadata for the image. So with those information, let's check out the data flow here. When we call the pull function, the client will get the manifest from the remote registry. And the manifest, it is used to store it is used to describe the structure of image, including layer data and the configuration. So when the client gets the manifest, he will store it into the content service. And then he will pass the manifest and try to download each layer data into the content service. But now we still have the raw data. We can use this to run a container. We need to unpack it. So the client will call the snapshot service to prepare a snapshot for each layer. And then he will call the diff service to read the layer data from the content service. You can see it here. And he will unpack the raw data into the snapshot. And then he will commit the snapshot. So over and over again, we can unpack each layer data into the snapshot. But now, we just have the raw data and the unpacked data. We still cannot use the image name to handle those raw data and the unpacked data. So we can see the final one is create an image. This action will create a record in the image service. This record will mapping from the image name to the raw data and the unpacked one. So someone asked for the list, right? So this is whole big transaction here. So we will use the list to log the raw data and the unpacked data during the pull function. So you can see in containerd, each component service are very small and very reusable, right? They can provide a very stable API to the user. So those components service can assemble together in variety of way to build any kind of function. So for example, if I want to change the pull function, change the data flow, so we can see when we get the manifest first, we will pass it, right? But we don't need to download the data into the content service. We can check the snapshot for the layer. If the snapshot for the layer is there, we don't need to download data. We can check the next layer. If not, we can download the missing layer data into the content service. and call the div service and a snapshot. So you can see we can change the data flow in the client side, which without changing any line of code in the backend side. So imagine that if we provide a general purpose API in the server side, we have no change, we have no way to do the customized things, right? So I think you might fork the repo in the record. In the local, you will maintain a very special branch. I think it is hard way to use Kubernetes because after several months later, a new version of upstream we came out with the very stable and very powerful feature. So at that time, you need to think about how to do the merge, how to do the migration, right? So avoid this case, Kubernetes provide a smart client. So those compose service can be reused to do anything. So we can see we have images service and a content service, right? We can combine it to provide a push function. So when you call the push, the client will get the image metadata from the images service, and then he will get the manifest from the content, and we'll pass it, and we'll get each layer data from the content service and push to the remote registry. So you can see those component service can be reusable, right? And besides this, Kubernetes client also provide an API set to control a container. For example, if you want to run a container, you can call the new container API first. This API will touch container service. This action will not run a processes. It just used to create a record, and then you can use the return variable to call the new task API. This API will touch the task service. It not just create the record, it will launch the Kubernetes stream backend server. As we mentioned before, Kubernetes stream is used to handle the life cycle of the container and keep the container alive if container D is down. So imagine that if we try to upgrade the running container D version, we need to shut it down and restart it. Without the Kubernetes stream backend server, the running container will be killed after container D is died. So it is very important feature here. So after Kubernetes stream is started, we can call a start API to run a real process in the backend. So we can call the start API here. So for now, we have a running process. So if you want to wait for it, you can call the vAPI. This API will block your current thread until the container is died. So we get there. If you want to clean up that container, you need to call the delete task first. It is used to shut down the Kubernetes stream, make sure there are no leaking resources. So this is how about the API set to control a running container. And besides this, smart client also allow us to modify the existing behavior, including service connection and the distribution. So this is how about the smart client here. And we can see Kubernetes has been designed to have loosely components, right? Those components can provide a very stable and very reusable interfaces to us. So we can see the smart client can assemble several components together to provide a very useful toolset library to do the integration. So we can see the general purpose API is in the client side, not the server side. So we can do a lot of customized things in the client side. So I think there's always a requirement to do in the backend side. For example, we need to support a new image local storage, like a QCode2 file system. And then we have a new generation VM-like container runtimes, like a gvisor, color container, and a Firecrack. So how could we integrate it with Kubernetes? And before I show you the solutions, And let's check out the plugin first. In Kubernetes, every component is plugin. So we can see here, and we have a lot of plugin here. And we have the snapshot plugin, content plugin, and image plugin. So for Kubernetes, how does it to maintain those plugins? And how to maintain the relationship between the plugins? So as I mentioned before, Kubernetes has been designed to lose component and clear boundaries components, right? With the clear boundaries, those components can be grouped together according to their own issue. For example, snapshot plugin has been designed to handle the local image storage issue. So we have the overlay FS snapshot and the device map snapshot. So we can see we can group those components together. So we have the category. With the category of the plugins, Kubernetes is easy to maintain the relationship between the different kinds of plugins. So look at this picture and look at this area. We can see the metadata plugin require the snapshot plugin and the content plugin. But for the metadata plugin, he doesn't need to know the implementation of the snapshot and the content plugins. So for the plugin itself, it is represented by the very stable interfaces. So based on this, Kubernetes provides a simple plugin registration mechanism. This registration action is very easy to learn and very easy to use. So look at this code here. And this code is used to register the bold metadata plugin into the Kubernetes. So you can see you only need to fill the form by the plugin type, plugin ID, request plugins, and the initialization. It will be okay. All the things will be done by the Kubernetes. And the initialization function will be called by the dependency order. So what is the dependency order? So look at this picture. We can see there's a lot of plugins in Kubernetes, right? And those plugins construct a very basic dependency tree here. So all the plugins will follow this pattern, and there's no cycling issue. And so with the plugin registry, we can easily to add a new implementation for the existing plugin or the new plugin into the Kubernetes in the code base. So we can see CRI Kubernetes is a project and also as a plugin, right? So we can easily for the contributor and maintainer to add a new implementation into the code base. But out of the code base, how can we integrate Kubernetes with the third-party plugins, such as the snapshot plugin and the runtime plugin? So Kubernetes provides two solutions here. First one, you can build your own Kubernetes boundaries. In Kubernetes, he provides a common entry point to set up a server by the Golang package. So you can use the Golang package to build your own Kubernetes with a fully function. And it is easy to upgrade the Kubernetes version by the upgrading Golang package. So no worry about missing any detail during the upgrading. So with the common entry point, you can register your own plugin into the Kubernetes. And let's check out the example here. So this example is based on a project from the Akihiro. And we can see the first Golang package is this one. It is used to provide an common entry point to set up a Kubernetes server. It is required. And the second group is provide our building plugins. Sorry. So it is required also. And the third one is the Linux basic plugins. So we also need to import this. So with those Golang package, we can build a Kubernetes. And the last one is the AUFS snapshot plugin. we can see we can add a Golang package and we'll register our own plugin into the Kubernetes. So basically, we put the registration action into the Golang initialization function, so that when we import a Golang package, it will do the registration. So you can see it's very easy to build your own Kubernetes, right? So I think you might don't like this way, and Kubernetes also provide external plugin. And for now, Kubernetes support two kinds of external plugin. One is the Proxy plugin, and other one is the external runtime plugin. So first one is the Proxy plugin. So when the Kubernetes set up, you will create a remote privacy plugin if the user try to configure it in the configuration. So for now, Kubernetes only support snapshot and content privacy plugin. But I know there's a lot of third-party snapshot plugin than other kinds of plugins. So for the privacy plugin, he only need to do is redirect the request to the external plugin. So for the external plugin, he has to implement the snapshot or the content for the content plugin interfaces. For example, look at this picture. This is for the snapshot external plugin. If you want to implement your own snapshot plugin, you have to implement those API in your gRPC service. So let's check out the example here. So if I had a customer snapshot external plugin here, first step we need to do is to do the setting to tell Kubernetes what is your customer external plugin and how to connect it to it. So you can see here, the customer snapshot is the ID of your external plugin, and the type is the snapshot. And the address, it is used to tell Kubernetes how to connect it to your external plugin. And in the second step, you need to export your own snapshot implementation as a Golang service, gRPC service. So fortunately, Kubernetes provide a Golang package to wrap your implementation as the gRPC service. So it is easy to set up your own external snapshot plugins. So before the Kubernetes start, you need to set up your external plugin first. So we can see we don't need to change any line of code in the backend. We can easily to integrate it with the third-party plugin, right? So I think besides the third-party snapshot plugin, we still have a lot of the new generation VM-like Kubernetes runtime here. So Kubernetes need to provide a mechanism to support external runtime plugins. So before I introduce the mechanism, Kubernetes was used to wrapping the external runtime command line to make it like a runc command line. So he can use the runc command line to call the external plugin, external runtime plugin. But each external runtime has their own abstract actions. We can do is we can cover all the external runtime plugin, right? And then if we use command, if we use a CLI to control external runtime, you will create an issue with the status with the container statement management, and each runtime has their own value. We can introduce all the existing code into the code base because it will make the Kubernetes out of control. So Kubernetes need to provide a mechanism to talk to each kind of external runtime plugin. So the mechanism is the runtime way-to API. We can call it stream way-to API. And this API allows Kubernetes to talk to the each kind of the external runtime plugin. And as I mentioned before, we know the life cycle of container has been handled by the Kubernetes stream backend server, right? So for each kind of the runtime, you have to implement their own Kubernetes stream backend server. We know Kubernetes backend server is a binary, so it must follow a non-link convention so that Kubernetes can find it, start it, and start it. So if you want to have your own runtime plugin, you have to implement those API in your Kubernetes stream backend server. So with the runtime way-to API, Kubernetes can talk to each kind of the external runtime plugin. So this is all about the solution here. So let's check out the demo. And first one is I will show you the integration with Firecrack. So hold on a second. Okay, it's good enough. Okay, Firecrack provides a naive snapshot to run a container, but this snapshot is a third-party plugin, so we need a privacy plugin here. So first step, we need to run the naive snapshot in the background. So I use the no-hub here. Can you see that? So I run it in the background first. Hold on a second. So we can check the status, right? So you can see it's up right now. So let's move to the next step, to setting the privacy snapshot. So let's check the configuration here. So you can see I named the naive snapshot by the FC naive, so we can use this name to call the remote snapshot plugin. So with this configuration, we can start the Kubernetes in the background. We also use no hub here. Okay, after Kubernetes start, we can use the CTR to check the snapshot status. You can see it is up and loaded by the Kubernetes. Okay, so we can use the CTR command line to download an image. So we can see we use the snapshot is the naive snapshot, right? And download a busy box. It will take a few seconds here. Okay, so we can run a container with Firecrack. So Firecrack is an external plugin, right? So it implements the stream way-to API here. So let's check out the naming convention first. So I run a container, use the FC naive snapshot here. And you can see I use the external runtime name here is the AWS1.Firecrack. Let's check out the result here. Oops. You can see it will show us there's no installed Kubernetes stream AWS1.Firecrack. So you can see if the runtime name is the x.y, he will convert to the Kubernetes stream xy. So you have to install, you have to follow this naming convention. Fortunately, I have the Kubernetes stream AWS Firecrack in my path, so you can change the name here. So you can see I can run the container with Firecrack, and so you can see in the container he used the guest OS. In the container he used the 4.14 here, but my host is used 4.18. So this is all about the first demo here. So next demo, I will show you the integration with Kubernetes. Let's check out the demo. Okay. So Kubernetes has introduced the runtime class resources, right? And we can choose the runtime for each pod, not just use the runC. We can use the gvisor and color container. But there's two concepts here. One is the runtime class name, and one is the runtime handler. For the runtime class name, it is used in the pods. When you choose the runtime class name in the pods, Kubernetes will send the runtime handler name to the container runtime interfaces. So, but for the container D, he doesn't know what is the container, what is the runtime runtime handler. So we can see, So we can see we need to do the mapping here. And first, Paul will use the class name, right? And the CRI will use the handler name. But for the container D, he had to know which kind of the runtime plugin will be used. So we need to do the mapping from the handler name to the external runtime plugin. So first step, we will set up a configuration here. So we will cap the configuration here. Hold on a second. So we can see the Kata container is the handler name, and the container runtime type is the external runtime plugin name. So if you choose the Kata container, Kata runtime handler, and container D will use this runtime type to run a container. So this will do the mapping here. So we can start the container D right now. So I use the service to start a container D in the background. So before you run a container D, you make sure the CNI configure is here. So after we start it, we use the CTR to check the CRI plugin status. It is up. So we can use the admin to set up your local cruisers. So it will take a few minutes here. So I use CRI socket instead of use the Docker shim. It will take a few seconds. We will set up etcd and kubelet. And you will run the 7 system pod here. Okay. So Kubernetes admin is okay. So let's check out the system pod here. But it will take 1 minute, so let's move on faster. We have 4 to go, 1 to go. Okay, all system pod is ready. So, but before we run the pod, we need to let my local host be schedulable. So before I create a pod, I need to create a runtime class resources. So let's check out the YAML file here. So you can see I created two runtime resources here. One is for Kata, another one is for gvisor. And this one, Kata, is the name of the runtime class, and the handler name is the Kata runtime. So as I mentioned before, I create a mapping here from the Kata runtime to the external Kata runtime plugin. So we need to create it first. So you can see I create 2 runtime resources here. And then I will prepare the pods here. Okay. And there's very normal pod here. So you can see we only add one field here is the runtime class name. It's a kata or divisor. So you will use the so this pod will use the kata runtime, and this pod will use the divisor. And let's move on. So I create a tuple here, and just a few seconds. Okay, anything's up. So I need to check out it is use the special runtime here. So I will use the uname to check the kernel version here. So you can see kata is using 4.4.19, and the divisor is used 4.4, and my local is used 4.18. So this is how about the demo here. So if you want to use the different runtime in your Kubernetes, you need to do the thing is you need to do the mapping here from the handler name to the runtime plugin name. So the last one is the advertising time. So new version with cans out. So first one, we will have the strong, powerful plugin ecosystem, and we will better support for the crucial resources. And the third one, we will improve our CTR command line. And the last one, we have a new idea around the image. We can make the image distribution faster. So that's all. Thank you. Any questions? Okay.
What do you mean about non-layers with the new version of containerd?
What versions, right?
The new version for container?
What version? Sorry.
The new version that is coming? Just the last.
Yeah.
Next one. Next. Forward.
Right?
Next. That one. Yeah.
Okay.
Non-layer. What does it mean? Like Docker layers when you build your images, or
No.
Or what do you mean with that?
For now, CTR is like a tool. It is hard to use. We will make very useful to help you to do the debugger things. Will not do the building things. If you want to use the build functionality, you can use the build kit. I think Kubernetes is very low level engine. We don't do the Docker thing in the Kubernetes. So if you want to use the build, you can use the build kit. So.
Okay.
Thanks. So any questions? Okay.
Thank you for your talk. My question is about Firecracker.
Okay.
So we tested this, how it works, in beginning of the year, and it was quite unstable for us with some errors. Do you know about current state? Does it have any issues?
Okay, you mean the status of Firecracker, right? What? You mean the status of the?
Yes.
For now, it's just like a prototype, right? Right now, we can use it in the CI. They are working on it. So I think it's just a prototype. You can just, and I think we can wait for several months. Yeah. Yes, it's I think we can now use in the production. I think we can wait for it. It's not stable right now.
Do you have any plans? Maybe need some help
No,
contributing to this?
I mean, Firecracker is from the AWS, not from the Kubernetes. We just do the integration with it. We not do the implementation in the Firecracker. Yeah, we just use it.
Okay, thank you.
So, thank you.
I still want to ask what is a layer means in your last page.
No layers?
What is layer means here?
Okay. So with an OCI image, right, you've got the base layer, you've got a manifest, it points to the layers that build it, right? When you want to create a snapshot, it creates one root file system for your container to run on, but they're pulled together to manage layers. Right? If you were to actually look at the tree of the images when you build your container image, it's got a lot of stuff in it. They're all copied on right, these layers, so that it'll be more efficient. Okay. You probably want to go back and how Docker does their container format. OCI picked that up, and when they say non-layered, I can only imagine they mean exploded, so that you can encrypt the whole thing and get one hash, the whole encrypted image, as opposed to possibly pulling an image from one other place. There's a lot of guys doing security stuff around these images. I'm not sure exactly what the non-layered means, but I can only think it's no layer, one image.
Okay, thank you.
They might have been talking about when it's local cache, because you pull them all in, you decrypt the layers, and then you put it on disk. Right? That's a non-layered cache image for a local snapshot on your host. I think that's what it's called.
Anyone? No? Okay. Thank you.